Hello everyone. Thanks David for accepting our invitation to talk here at CosmoVerse. David Wiltshire is a professor of theoretical physics at the University of Canterbury in New Zealand. He obtained his PhD in relativity and gravitation group at the University of Cambridge in the UK. He then held research and teaching positions in Italy, UK and Australia before returning home to New Zealand in 2001. His research began with black holes, higher dimensional gravity, string theory, brane wars, and quantum cosmology. Then he moved to theoretical cosmology, working on modified gravity, quintessence, and nucleosynthesis. And now his focus is on the averaging of the inhomogeneous universe in general relativity, cosmological back reaction, its implication for the dark sector, and the foundation of theoretical observational cosmology. Today, he will present exploring the Hubble tension with dynamical spatial curvature. David, you can start, please, when you're ready.
Thank you, Leonardo. So it's a great pleasure to be able to give this seminar. My title, Exploding the Hubble Tension, is related to the fact that we're actually talking about standard explosions, supernova, but there are other, the way that I'll be doing it is quite different. Right, so extraordinary claims require extraordinary evidence, and the extraordinary claim I'm making today is that the cosmological constant problem, there is a solution to it. The cosmological constant, we all want to know what it is. I'll say it's a counterterm in the theory, in the sense of quantum field theory. In fact, you can regard it as a running coupling. It is there, the counterterm balances the all-sky monopole average of what I will call the kinetic energy of expansion. It is the kinetic energy of expansion of negatively curved voids, which come to dominate the universe at a particular time in its history, and they're dominating at the present epoch. Making such extraordinary claims requires that you have some essential ingredients. And in this case, the ingredients that go into the Timescape model I've been working on for 17 years or more, a little. And those ingredients are, first of all, you need to have a realistic spectrum of initial conditions. So if you want to make an extraordinary claim, it's got to be a compelling claim. You're going to need back reaction of inhomogeneities, the fact that we do live in a universe dominated by voids. And this back reaction here means an expansion which is not Friedmann-Lemaitre-Robertson-Walker on average. So there might be a close to Friedmann evolution patch at each point at each section in history, but the average overall is not Friedmann. Now, and the important third ingredient is what I will call the quasi-local uniform Hubble expansion condition. And this one also deals with the Hubble tension, but in seeking, when you deal with inhomogeneity, it's actually very easy to deal with the Hubble tension, but you have to do it in a compelling way, and this is what I claim. So doing this requires extraordinary evidence, and the extraordinary evidence that I'm going to present today is actually 1 to 3 years of analysis by a number of talented PhD students. A couple of them might be on the call, Zach and Chris, although Chris is on a ferry going to the North Island for his holiday at the moment. But Michael Williams has been leading the analysis of the simulations of Haley-McPherson. So Haley McPherson co-supervises Michael Williams. Haley, of course, is now in Chicago. Michael is here. So the way that I'm going to present this talk is I will first give a brief overview of the Timescape model, the whole setting, and then I'm going to present results and speak to how those pieces of evidence fit into a big jigsaw puzzle, and we can now see, at least I can now see, the things that make up the whole of that puzzle, starting to. It's just steps in this direction, because of course there are many layers. Now, what I'm going to present, I would say that not everyone, not all of the co-authors necessarily agree. And the whole way that I approach things is I want to have students and colleagues who will argue with me about everything, because that's the only way that we make progress in science. So these are my views. Not every view is held by everyone necessarily. So the situation we have, there are sociological implications, and we have one Roy Kerr in our department. And what every theorist dreams of is that you're spectacularly right just once, and then all your other crazy ideas are forgiven. So that's the sociology that underlies the way that theorists approach things. Roy is still here, so and he's still contributing. So just for everyone who doesn't know that, yes, Roy Kerr is still alive, and he's going to turn 90 on the 16th of May. And this was a photo last Sunday. Roger Blandford, who shared the Crawford Prize, happens to be visiting, and we had a lot of really interesting, fruitful discussions. So there's another sociology that goes on in terms of observation. And on the left, we've got Joe Weber. On the right, we've got another thing. And that sociology is that if you're spectacularly wrong just once, then all your other meticulous measurements are forgotten. So to be a successful observationalist or experimentalist, you've got to be super critical of everything. However, this leads to a bit of a dichotomy in the community, because observationalists are also really conservative often about the underlying theory, and trying to bridge these two communities, and which is what I've been doing, starting out as a theorist, and I'm still a theorist, but I've had to talk to observationalists more and more over my career, and that has led me to very different ideas, and it's led me to looking at foundations. So what's in a theory? So what here in our Maoris and generally Polynesians will call the whakapapa of a theory, the layering of a theory. It involves a number of things. It involves concepts, involves phenomenology. So concepts, that's the things that philosophers and theorists talk about. It involves repeatable experiments, and it involves writing the above in equations. Right? So lots of cultures have had concepts and phenomenology. Many cultures have had equations too, but all of these things go together to make up a theory, and in the sense that a mathematical physicist uses, and those go through in layers. If I think of one example, let's think of the example of quantum mechanics. Well, there's a concept of the atom, and that's almost many cultures have that one. There's phenomenology, in this case, Rutherford scattering. So our local hero, Ernest Rutherford, who appears on our $100 note, that led to the idea of the Bohr atom, so the central nucleus, and most of the atom being empty space. But it took it took over a decade, actually, before we had the Schrödinger equation, the Dirac equation, the Barber-Wigner equations, and the equations of quantum field theory. So that took a long time. And what I would say now is that we are in the middle of a paradigm shift. That's a bold claim, but and it's that. What is that? It's going to involve quantum gravity ultimately, and I think we're now that we've got data, because we need data in order. Physics is a data-driven science. We need data. So this is the way that the model that I have is been progressing. So first of all, one had to have some ideas, and those ideas, until you've got a phenomenology, well, you need phenomenology, actual predictions which agree, and the phenomenology requires data, and some of that data is coming now, and it's coming very fast, and there's so much of it, and all of those things are needed before you can have the theory of quantum gravity, and those things are beginning to be understood, and the more that that the results are coming in, the more that things are coming together. I can now see things slotting into space. So dark energy, dark flow, dark matter, dark flow. Well, I won't talk about the dark flow so much in this talk, but we'll get to. Well, there are questions also. So that at the end. Okay, so people want the whole reason for CosmoVerse is that there's tensions, there's cosmological tensions. Everybody wants a revolution. And the revolution, I believe, is seen in some various pieces of data. And what we're doing here is, I'll talk about later, but what we've seen as signals of something, first of all, in Pantheon Plus, the data. It will, of course, be there in all the upcoming surveys, and that's why we have to, the supernova, DESI, all of those, that's why we first went back and looked at this, because now that Pantheon Plus is able to pick out certain things in the data, and I claim if you look at the lowest one here, that's the Hubble tension before your eyes, because there is a discrepancy, and that discrepancy is due to a certain sensitivity, and we can see that doing the Bootstrap and doing resampling, and now at least we can see why things are happening as they're happening. Now, the Euclid satellite was launched last July, and the Euclid satellite is going to falsify the Friedmann equation, or alternatively support it. And in doing any phenomenology, and you've got to have, having a serious theory, you've got to have predictions. And I have had such predictions since the 2000s, and in 2012. So this involves something called the Clarkson-Bassett-Lou test. I won't have time to go into all the details, but essentially, if you've got the Friedmann equation and differences from it, then you can, this is set up as a null test. So there's a certain curvature statistic you can calculate, and there are different models of back reaction you can have. You can have the Timescape model, the blue line, the TARDIS model. You can have a unfalsifiable model, such as a large void, which wouldn't be much good in this, but it would be ruled out for other reasons. So the projections for Euclid were made in 2014 by Friedmann-Lemaitre-Robertson-Walker, and so within 6 years, perhaps even before that, because the data is already coming, and will be coming soon. I mean, then we're going to, either Friedmann is going to be ruled out, and maybe I'm going to be ruled out, and then I can retire and do something else. But I mean, I'm happy to place a small bet on it. I placed a bet with Padmanabhan. Unfortunately, Padmanabhan died, so he was unwilling to repeat the bet that we had. But anyone who wants to make wagers, I'm happy to make a wager. So what's in this revolution? Well, there are a lot of things in here. What is the origin of scale? Where is infinity in terms of Carter-Penrose diagrams, spatial infinity, time-like infinity, etc.? Why is there average isotropic Hubble expansion? What picks out which is homogeneous apparently when we have anisotropy on smaller scales? Why is there transition to homogeneity empirically around a certain scale? Well, the Friedmann model assumes all of the above, but certainly in the 20th century, physics should explain the above. And that's what I'm claiming quantum gravity is going to do. And that's what I'm claiming, the bold claim, that the cosmological model I'm presenting does. So the time is now, and certainly I don't have all the answers, but I've got questions, and each question is raising another question. These are raising questions about, very prosaic questions about astrophysics. Is the dust in other galaxies the same as ours to within a standard deviation? Well, it always had to be in my model, and if it is, then things fit. So what I'm going to introduce and talk about in this talk is not so much all the astrophysics. I don't have time for that. But I'm going to look at what I call the role of non-rigid spatial curvature. So what I've done here is simply cut and paste things from a grant proposal, which I now got. It's fantastic to finally get that grant after 11 years of applying, but people had to wait for things to be happening. So dynamical spatial curvature is going to involve the kinetic curvature, and the kinetic curvature, whoops, is not something which scales according to a Friedmann expansion. So in the Friedmann model, we have what I would call rigid spatial curvature. It scales as up to a sign, because negative spatial curvature corresponds to positive energy, positive kinetic energy, I'll claim. And so it's not going to scale as 1 over a bar squared, where this is some average constant. Instead, the kinetic curvature scales proportional to something called the void fraction. The void fraction is tiny and early on. It's going to be of the order of 10 to the minus 5. It's going to be consistent with the power spectrum. So because this void fraction goes as, well, it's the cube of volume, so this is a volume void fraction, we have a behavior which is different to what people are used to in the standard model. And this kinetic curvature, it starts off small. This is the very, very early universe here. Everything looks the same, very close. It's very tiny. There's a very tiny difference. The tiny difference is of order 10 to the minus 6 at near the surface of last scattering, and that's around here. And then up to here, we have what looks like an Einstein de Sitter universe. And then very late on, the kinetic curvature dominates. Matter fraction goes down. And this is what we would normally call dark energy in the standard cosmology. There's an amount of back reaction that is needed, and that amount of back reaction is very tiny. In fact, it looks like a positive spatial curvature, because you might say it's in the actual equation, it's what is there because of the formation of structure and matter and galaxies and etc. So there is a sum rule, and the sum rule that we just saw in this for these quantities here, it's a running, and so at the present epoch, we're going to have, whenever you go into a model with back reaction, there are bare quantities and dressed quantities. And there is going to be a sum rule here, and the sum rule is for the bare quantities. So this is not, you cannot compare this directly to omega lambda. There are dressed parameters, and the dressed parameter will give things which are very much like omega lambda. But the important thing is that the kinetic spatial curvature is the thing that is replacing dark energy, and it is a counter term, and you can add this counter term to renormalize the direct, the zero of your potential away to zero, and everything else still works, and the whole thing works. And so in general, there is going to be an average Hubble expansion. So here I'm comparing 3 different ΛCDM models, and with different parameters, but the average expansion is always flatter because it's close to a void-dominated universe, and the void-dominated universe is empty. And so this is going to be flatter than the average Hubble expansion usually is. There is going to be a effective co-moving distance. So here, the black line is the Timescape model. If we fit it to the angular diameter distance of the CMB, then it best fits. So here it's designed to best fit model 1, which is the model which best fits the CMB. Model 3, at low redshifts, it is the one which best fits supernovae. So there's always been a tension between supernovae and, when you overlap things, they're within the certain sigmas that you require. But what it does is it interpolates between different ΛCDM models. And each ΛCDM model there's a certain shape to them. And the shape, people then try and force into something known as the equation of state parameter. But actually, if you don't have something which is an equation of state of a fluid, then you don't get a simple W. Well, that's another talks. So I will skip over those. I want to get to the results. Okay, so redshift. Redshift is the other important thing that we measure. And it is the ratio of, so 1 plus the redshift is, of course, the ratio of wavelengths and energies and frequencies, and involves the inner product of a 4 velocity of an observer and emitter, and the k, the wave number or 4 momentum of the photon. And you can do various approximations. In astronomy, people often just use the radial Doppler effect, but you can also go away and any ratio like this, you can split into other ratios by, so there's a U naught here and the U one there, and so you can just split it as you wish. And this one is done in a way which is the same if you go and look up supernova cosmologies. Some years ago, Tamara Davis and Calcino did the same, write down the same things, because of course these things are very important in what people do in general. So these ones you'd call peculiar velocities, and if you look at the one in the middle, if you adapt things to observers who are at rest, then there's a cosmological piece. Now this cosmological piece can also include an arbitrary overall conformal frame factor, which is because photons don't see the scale. You can divide top and bottom by something at each point, and there is a degeneracy there. So if you divide all of those things in general, so we've got what you'd call gravitational potentials usually, and those are considered to be small in the standard cosmology. And then the bit in the middle here is the average expansion. The average expansion involves particular ratios. And you can look at these terms, and in the standard model, of course, you've got the usual scale factor. In the standard cosmology, these gravitational potentials are of order 10 to the minus 5. Now, in a lambda-Zechariz model, which are the ones that I'm not going to have much time to talk about today, these can be 10 to the minus 3, and everything is still consistent. And this is actually going to be closely related to other things, the quasi-dipole anomaly and all of that, which we're working on and are very close to solving. Now, in the Timescape model, there is a null cone conformal frame degeneracy, and that null cone conformal frame degeneracy allows you to have all of these different runnings, and it's running couplings effectively if you're looking at things from the field theory viewpoint. And what is important in that is that there is the Bondi-Metzner-Sachs group, and that is relevant now in a lot of things involving gravitational wave production. And it's relevant in a lot of things, and then involving string theory, and all of those things are coming together, and it's here. And I can see foundationally, because that's the ones that I started with, that those things are relevant, and we need everybody to put these ideas together, because it's really cool and it's really exciting. So all I'm going to deal with are, I just need two things: distance and a redshift. And so we're going to have models which are going to satisfy the Etherington relation. So there's going to be angular diameter distances, luminosity distances, and the Friedmann model, you've got certain relation for the co-moving distance in terms of these hyperbolic functions, or a sine function if you were to have closed universe, etc. And in the Timescape model, you've just got different things. So it's very different, but this comes, there is an exact solution. The exact solution was in PRL back in 2007, and you just, there are different numbers, and there's Baire parameters and Dress parameters, and you've got to worry about all of that. But the thing is that you've got a model you can write down for the average evolution, and it is quite simple. So the evidence. The first thing that I'm going to talk about is work with Zach Lane and Antonia Seifert. So student here, Zach is a student of mine, Antonia is in Heidelberg, and she came as a summer student a year ago and was here for 4 months. Now, the residual distances in the Timescape model and the ΛCDM model always have the feature that Timescape is flatter than ΛCDM. It's related to some things, the cosmic coincidence problem and all of that. And what we've been doing is the Bootstrap and doing random resampling. So looking at random subsamples and drawing them. And what we've been looking at is for convergence. So the Bootstrap is an amazingly powerful technique in statistics. And you can check to see whether your things are converging. And if they do converge, that's fine. If they don't converge, well, it shows there's a problem. And if we look at the right hand, these panels here on the right, then okay, that's converging because the uncertainty is within that uncertainty of the purple and the blue. Fine. Oh, there's a problem here somewhere there. Somewhere there's going to be things that do not match where the final thing does not match. And what we're looking at is the trip relation and how things are converged. And what we can see is that Pantheon Plus have done an amazing job. So Dan Skolnick and others, what we've been able to see is that there were results. There was a debate between Nielsen, Gufanti, and Sakar, and Rubin and Hayden and others. And what people have been trying to do is do the best they can, but everyone makes different assumptions. And what we can now say is that we understand why those people made different assumptions, and everybody was right in some particular way. And we're beginning to understand why all those arguments took place. And we don't have a lot of time to go into all of these things. Zach will be on hand to answer questions if we want to talk about some of the fine details. But what we can see now, if we look at convergence of something such as alpha, this one here, what we can see, things are converging. So what we're doing here, I should explain, is we are taking the whole sample and then cutting out pieces of data. So in the trip relation, which I didn't bring with me to this lecture, in the trip relation, one recalculates the cosmological parameter or parameters together with the empirical light curve parameters. So the stretch and the color. The color is related to the peak magnitude, which is mainly produced in the main transition involves nickel production in a type 1a supernova. So there's the trip relation. You've got the empirical light curve parameters. They are put together with the cosmological parameter, and then you compute something for your entire sample. And that, if you do that, things should work out in the sense that there are some things which should be global parameters, and you expect to see convergence. Well, I don't have enough time to talk about all of those things, but anyway, what we do now see fine structure in those relations, and we can look and see, are things stable? So yes, things are stable now. And when they were, in terms of the cosmological parameters, they're just stable to slightly different values, right? And but ΛCDM and Timescape are both stable. Timescape gives, so that we have different parameters. There is the void fraction. The void fraction is the fundamental function in Timescape, which should be compared to omega matter. In fact, so you can work out a dressed omega matter, which has the same sort of, from the void fraction, you can work out a dressed omega matter, which is just something which is chosen so that we can draw things on the same scale. and make sense of it. It's not that the dressed omega matter is not a fundamental parameter of the timescape model. It is it's the void fraction which is. So we see sensitivity, convergence, all those things make sense. And here, what is important is not each of these points in this model represent, so each of these points represent a different model. So what we keep on doing is throwing away all the data below a certain redshift. And essentially, this is what Rees et al. Did in the earliest work with the gold sample back in 2007 and with the MLCS 2K2 methods. Is people say, well, we know things are not in the Hubble flow below a redshift of 0.023, I think it was, and so we won't use that data, and we'll just go and work out the properties of the supernova that we need, and then use that further on. So here in the blue area so this is the logarithm of the ratio of the likelihoods, and if you were in the white area, there's no more than a bare mention of any success. In the between 1 and 3, it is positive, and over 3, so over between 3 and 5, this is the Jeffreys scale, and you want to be over 3 to be really sure. And here things are only tentative still, but what's important is the integral under the curve. So each of these different models, if you're doing a Bayesian comparison, you're looking at all of the possible different models, and here we're cutting stuff out. And the integral under the curve, even over here in the Pantheon plus full sample with, so this includes, so you have supernova, which are seen with different telescopes. So this is all the historical data. And of course, there's much better data now, but we need to understand the systematics, understand how to put things together before we can go apply these methods to the new data, and then we can really test and compare things. So the integral under the curve, it favors Timescape, even for this full sample, just marginally positively. But what's important is that this difference here is exactly this is the Hubble tension before your eyes. It's because you are using a degeneracy in your data between and when you use that degeneracy at this redshift, and it all depends on do you include data which is close, which is at small redshifts or not. So the interesting thing, when the students came and showed me this, and they said, well, we're not sure if you'd be happy with us. I said, no, that's amazing, because here where the timescape went below this, according to Rees et al. Back in 2007, we don't know what's going on there. But in the timescape model, there's something called the quasi-local uniform Hubble expansion condition, and that applies right down to the scales of about a few megaparsecs. And so on the small scales, where nobody is supposed to understand what goes on, the timescape model is predicting things better and almost going over here. So this is exactly what I would expect to see if it worked, that it's working really well. And I said, gosh, that's amazing. And it's because it's working here, and because it's working there, we can now know what the next steps are. And in fact, the referee has suggested that we do some improvement, and which Zach's got the code still going again, I think. So the revised version of this paper, I'll just wait until you see the revised version, because we might even do better on this paper itself. But it'll be after this weekend, I think, still. Okay, so there are the likelihoods and the random resampling, and those are the parameters. And these are, it's fitting at a void fraction of 0.76, and that's the same void fraction that I get independently from the CMB. It's the same void fraction which we're going to see is picked out by strong gravitational lensing even, which we're coming to now. So this is the work of Chris Harvey-Hawes and myself. And so strong gravitational lensing, we can go and look at profiles that people use, and we can look at the ratio of distances, because the ratio of distances is something that is clean. If you have very good distances, of course, that's excellent. But if you take the ratio of distances, then in terms of the Timescape model and the standard model, both of those are giving something which is a very simple thing. And there are simple model parameters that people have for their lenses. And so there's something known as the extended power law model, which is very Baroque, but basically inside there's density of all of matter. It's got a certain profile. So these are just empirical power law relations. There is the luminous matter, and then there is the fact that actually you've got to account for velocity dispersion, and you're taking an average of, it might be elliptical galaxies, etc., and you only get an average spherical thing by taking averages of things which aren't spherical, and you look at velocity dispersions, etc. And this is a very Baroque, and it involves a lot of stuff that goes in there. But if you simplify it, then you get down to spherical power law model, or the simplest thing, the simple isothermal sphere. And the simple isothermal sphere model is used a lot, and you can go away and look at the distance ratios in terms of the Einstein ring, and go away and relate this to empirical things and matter, and deduce a lot of things. But it turns out actually that the mass models are not that great, and that people have to go away and compute things for individual galaxies rather than taking averages. And so what we've done is we've gone away, and a problem with those mass models being not so great is that the chi-square per degree of freedom is 2. And in order to get a chi-square per degree of freedom of 1, people go away and they do a fitting. And if you fit enough, you can make the chi-square per degree of freedom back to 1. But then, you've fit a lot of parameters of each individual lens differently. And there's got to be some question about what you're doing there, because are you looking at the mass just in the galaxy, or are you in the cluster of galaxies? Are you looking at stuff along the line of sight and putting it into the model incorrectly? So what you can do, and we've done, is you can go away and fit with a wide range of priors. So you can go away and do MC simulations and see, do you get your parameters out? And in general, what you find for Friedmann, so you put in some parameters, and we start with parameters in each case between 0.1 and 0.9, say. If you want to start off with things in some reasonable range, well, the universe isn't empty, so it should not be driven. You should not be driven to have an empty universe. Unfortunately, Friedmann, it will always, so if you start off with 0.9, you end up lower. You start with 0.6, you end up lower. You start with 0.315, so close to what we believe from other things in the Friedmann modeled universes that we live in. We start with an omega matter parameter of 0.315, but then we're actually driven to lower values there, and you can actually be driven to 0. Why? Because voids that's the only way that you can get close to a void-dominated universe in Friedmann. Timescape, you start with these things, and the same modeling procedure, MC simulations, you're driven to 0.73, it turns out. that's within the standard deviation of the 0.76. So we start with 0.76, we end up with 0.73. Those are the numbers that come out from the CMB. Those are the numbers that come out from supernova. There are other things as well, actually, things that many, Peter Smale went away and looked at other distance indicators over a decade ago. Now, so those are independent measurements and they fit. Fantastic. You can go away and try and fit if you use different mock catalogs, then you find, well, things are driven in such a way that, okay, so the last is, if you fit the best fit parameters to data, so Friedmann fit to Timescape data, Friedmann fit to Friedmann data, Timescape fit to FLRW data. And the first one was Timescape fit to Timescape, but in each case you see what comes out in terms of your prize and things, and there is a consistent story behind those things. There's interesting stuff that goes on if you look at you have actually unphysical distance ratios in there, and some of those are, those you cannot have a situation in which your lens is behind your source, but some of within the uncertainties there are those parameters around, and so again we see a consistent story about when those unphysical ones give you unphysical results, and there's a consistent story in that it drives things to a pure Einstein de Sitter universe, as we would expect. The real icing on the cake is this one, and I will not have a long time to go through it, but so Michael Williams has done simulations. He's not done the simulation, sorry. So for the first time, we have the void statistics in numerical relativity. And we have the tools to relook at the simulations of Haley-McPherson. So these are the same simulations which people have been looking at, and only with the right tools, we can now see the signature of spatial curvature. It is there and inside the same simulation. So, and I think it would be great if Michael actually gave one of these in future, because there's so much in here. So we had to have, so there are voids, there are filaments, and we had to have the right way of finding the void. So we got a watershed Einstein topography finder, a version of the watershed algorithm. It will be on GitHub, etc. in future. So we have ways which you can do now, developed by Michael, working with Haley, and we can go away and look at the distribution of voids in the simulation. So these are the same simulations that give an Einstein de Sitter universe if you take your averages in a certain way. And it's a bit surprising, well, if they give us an Einstein de Sitter universe, where's the curvature? Well, the curvature is the kinetic expansion of the voids, and you can always renormalize the 0 point, the asymptotes. So what we can go away is we can go away and do the void statistics, and there's beautiful things that are happening with the void statistics. And as expected, so the density contrast agrees with what we expect for looking. So what we're doing is stacking voids, all of the voids in the whole simulation. So the same simulations that Haley's had for years, just we did not have the tools previously to do the void statistics. And you have to, so one important thing is that you have to actually be able to say, well, what is a void and what is a wall? Because if you take some random box you're going to get the average, but if you want to work out what's the kinetic curvature, you've got to be able to stack the voids in the right way, and that's understanding, well, do you take the distance from the wall or the distance from the center? How do you define the center? How do you fill things up? There's a lot of technical, really interesting stuff about the numerical simulations which has been done, and Michael has done all this, put it all together, and the whole thing there. So this is the curvature. So and the curvature is negative, as you would expect in the void. So in the standard model, these are supposed to compensate in exactly in a certain way to give you 0. So, but it's consistent, and it's consistent with the Timescape explanation. So this is the kinetic curvature that comes out from the simulation, and the 0.86 is consistent with this way of stacking. So the kinetic curvature, I claim, is there in the simulations. It's been there, but no, we did not have the right tools to look for it before. We now have the right tools. The curvature, which is assumed to be 0, is assumed to be 0 because you can get rid of the monopole with a counter term, and it's the gradients of the curvature which give the dynamics. So it's the shape of this which is very important, and it's the shape of this. So gradient of potential gives you force in Newton's theory. Gradient of the source, the kinetic curvature, gives you the dynamical curvature, and so we're now looking at those things in a deep sense, and involves quantum gravity, and it's going to involve things such as helpful things are the Newman-Penrose formalism. This is my former student Nezzy here at work one day back in the day, and if you want to look at things in quantum gravity, you've got to look at really complex problems. And so each piece of the puzzle is there to be understood, and it involves things like the bonding Metzner-Sachs group, a whole lot of things. But we're beginning to understand and see what those things are. We have a team here at the University of Canterbury. So this is our group in front of the Rutherford building, of course, our local hero, Ernest Rutherford. And and we're all working on different pieces of the puzzle, but it's much too big a problem for just this one group to be working on. It really involves everyone, everywhere. Marco Galoppo, here's a recent paper with Federico Re, which is on arXiv this month also. So there are relativistic galaxy models, and they failed. Why did they fail? Well, we've got new results soon, because you have to understand why things failed, and then you can make new things. And actually, there's some really interesting stuff about to come. Morag is looking at the quasi-dipole, the Ellison-Baldwin thing. She's been using Asta Heinesen's formalism. Asta is, supervising her, Asta being a former student of mine now at Niels Bohr Institute on his second postdoc. So dark matter, yes, dark matter, we're beginning to see how that fits in. When you open Pandora's box, there's loads of questions. There's fundamental questions about supernova, light element abundances, BO extraction. Then there's the theory, and that's the theory that we're heading towards, in my biased, humble opinion, and involves a number of issues. And the most important, interesting one is, what is the geometry of the Higgs mechanism? And the underlying geometry probably does involve things like Kaluza-Klein and string theory. I'm now beginning to see, but we have to think about those things differently. So that's where I'll finish up and ask for any questions.
Thank you. Thank you so much for the very nice talk. Marina?
So thank you, David, for number one, working in close connection with the observational cosmology community. I follow your work since 2007, and I have observed the lengths that you have had to go in order to recalculate all sorts of observers in cosmological probes for yourself and work out what the signatures would be according to your model. it's a huge effort that nobody that I know would even consider putting themselves before what you have been able to achieve. And today, I work in quantum gravity and in cosmology, and when I see in completely different physical regimes, in classical mechanics and quantum mechanics, in complex systems, you touched briefly of fluids, the fluids approximations, numerical relativity. I see signs in those communities of the puzzles that you are addressing in cosmology here. And so when you make briefly a touch with quantum gravity, and I want to herald David's work and his perspectives, because I see signs outside of cosmology that these questions will solve numerous problems in physics, including the road to quantum gravity, including the solution to the measurement problem in quantum mechanics, and the Navier-Stokes fluid approximation that are all under threat. And so as well, the Hubble tension work is incredibly relevant, and it will help us understand how to view the universe at very large scales. And I want to say that David's work goes even beyond cosmology, the implications of his work. Thank you so much, and I hope you continue with all the support to continue the work that you have been doing.
Thank you, Marina, for that very kind summary. What I must stress is, I think the problem of quantum gravity is so big. I mean, quantum mechanics itself took so many people over a couple of decades, and this problem now doing quantum gravity, it's the whole universe. We need everybody to work together, because really it's if people involved in quantum gravity, you could count on two hands or three hands. It was more, but there's so much data, so much is happening, and really this is a time when everybody has something to contribute, I think, and it's the beginning of decades of work, I think. So it's I think we really are at a point in the development of science where there is a paradigm shift. It's not one person, no one group can do it. We really need everybody to pull together and figure this out, because it's amazing. We're lucky to be here now. That's all I can say.
Thank you. And any other questions or comments?
Yeah, I should say also, it's just good to have two models to work on. One problem is when people just have one model and keep on fitting it, and there has been a lot of sociological pressure because people want their next grant, and that's always, in any genuine paradigm shift, it is always like that. So, just having two models means that you can test things and compare things, and then you find new things out about astrophysics even. So you don't have to say this is the answer, because in fact it's not the answer, it's just a step in many layers of questions. But just having two models to compare is really a good thing. It's healthy for science.
If we have more time and there is no questions, I would ask David if you could speak, or if you are aware of the work on the Navier-Stokes regime in classical mechanics. There's a new PRL out by a John Hopkins team that is
I'm
very...
not aware of that.
Okay, let's take it offline. I will put you in contact. It's a dream of mine to put you in contact with these guys, but I know you're so busy.
Thank you. Yeah, no, I'm looking. There's really other interesting stuff about. So, I was talking a week ago with Anke Ardern-Aronson about the Pristine survey and primordial lithium, and so they're looking at calcium signature. Anyway, so light element abundances, there's some really cool and interesting things where I can expect to see something different depending on the local environment. You know, lithium is easily photodissociated, and you just need to have enough environments in the early universe. Well, anyway, that there's a really interesting thing that I only found out about a week ago. So
There's a
totally
question in the
hidden.
chat. What
It's not
develops
true.
the large voids if the model is similar to lambda dark matter?
It is just the primordial spectrum. So it is the model, well, it is, so the primordial spectrum comes from the primordial density fluctuations. It's just, so they're not compensated to a Friedmann background. There is a tiny difference of, so I've got the parameters. So if you look in the paper with, so our last archive paper with, so Williams, McPherson, Wiltshire, and Stevens, this one, I've got the initial conditions there. So a tiny void fraction of in the order of 10 to the minus 5. It's just the same. It's the same physics almost to the standard model, because there's no lambda. Lambda is not important in the early universe anyway. So it's just that it's not compensated. So there is a difference of order 10 to the minus 6. Right, so there are tiny differences, and when we go, if this is to work out, then in future, those tiny differences we can start to probe. But the most important one, of course, is lambda, and that's just there to scale the box in the standard model, and it's the same matter power spectrum. So the matter power spectrum is the one we have. It's just, it's not compensated to a Friedmann background. There's a tiny, tiny difference.
Okay, thanks. I can also look at your papers, of course, but
Yes.
yeah,
So,
thanks.
so the paper, Michael Williams et al. is the icing on the cake as far as I'm concerned. That is the one that I want, that had to be out before I gave this talk. Wouldn't.
Right, thanks. And I'd also like to add, as Marina had already said, it's very valuable what you're doing. So,
Thanks, Pavel.
yeah, thanks. Thank you.
I appreciate your work too, Pavel.
Well, thank you. Yes. Yes.
It's interesting. Yeah.
Okay, thank you. Any other questions or comments? No? So let's thank David again. Thank you so much.
Cheers.